Hi everyone, my name is Eyes and I am a PhD student at UC Berkeley. I'm joined today by my co-author.
Hey everyone, my name is Entropy. I'm a PhD student at the Duke University.
And we're going to talk about ProSE, the architecture and design of a protein discovery engine. In recent years, artificial intelligence has really revolutionized protein design. It's led to advancements in structure prediction, fitness modeling, and beyond. However, it simultaneously created a new bottleneck within research, which is the intense computational requirements of artificial intelligence. This is particularly true for what's known as in silico design, where we're trying to explore a combinatorial sequence space that's non-convex, much like this one here on the right. This is particularly the case within drug design, which in 2019 was about an $80 billion annual effort and had around a 90% failure rate. And so we have to ask ourselves, can we accelerate the protein artificial intelligence that can really revolutionize drug design? To outline today's talk, I'm going to cover protein BERT transformers, their use cases and profiling, as well as talk about the length problem in transformers, which is the big motivation for our accelerator. I'm then going to hand it off to Entropy, who's going to talk about the microarchitecture and data flows, as well as some of our results in speedup over the 100 and TPU-v3. And to help you keep track of the novelties, we're going to use these stars to designate major novelties in ProSE. As a bit of background, we're going to be looking at BERT-style transformers, which are very common within natural language processing. They're really powerful because we can take a model and we can pre-train it on language data, which is then used for downstream tasks. And the way this works is we take in a sequence, oftentimes a sentence. We use these to kind of pre-train and predict the next token in that sentence. And then we can actually get the feature representations and use those representations for downstream tasks. Things like search, question answering, translation, and other common tasks within natural language processing. Within protein BERTs, we're going to do something very similar, except we're going to take in a protein, convert it to its amino acid sequence, and then again pre-train it to predict the next token in the sequence, and use the learned representations to predict downstream tasks like structure prediction, stability, or binding affinity, which is the one we're going to be focusing on today. And for those who are familiar, you might recognize that AlphaFold 2 also used a modified BERT-style transformer, albeit for a slightly different task of structure prediction. We also included a simulated case study to evaluate the ranking accuracy of a protein BERT workflow. Our downstream task, again, is binding affinity, where we're actually trying to predict the strength with which a monoclonal antibody binds to its target. The target in this case is the HER2 receptor, which is a well-studied cancer target in HER2-positive breast cancer. Our workflow is fairly straightforward. Again, we're taking in a sequence, learning a set of representations, and then using those to predict binding affinity. Even with a very limited fine-tuning data set of only 39 examples, we can actually still achieve a ranking accuracy of about 0.55 on a held-out set. And we can then use this workflow to screen millions of sequences with AI by simply mutating the inputs a little bit and searching over sequence space. And the best part about this is that because this is an AI workflow, as soon as we get a better protein BERT or a better model, we can swap that out and simply automatically get that gain in performance without the need for manual intervention. And now we've talked a little bit about the benefits of protein AI, but there's this big issue, which is the length problem. And this is kind of summarized by the fact that protein BERTs, while they're revolutionizing protein design, aren't really well supported by existing accelerators. This is partly because accelerators target convolutional neural networks and not transformers, but it's also partly because those that do target transformers have a few key differences in protein BERT versus human language BERT. While human language is often 32 to 256 input tokens, we actually see that many medically relevant proteins are much, much longer, between 512 and 2048 amino acids in length. This includes things like monoclonal antibodies and cell signaling receptors, which are both the inputs and target. As for why this matters, it's actually because within protein BERT and human language BERTs, the workload is very length dependent, and so we can take an already very computationally intensive AI model, and then we can see this quadratic increase in runtime as we increase length. And obviously, we would like a lower runtime, and so a flatter curve would be ideal, but that's just not the case of how these models work. And in addition to this kind of quadratic increase in runtime, we actually see a very significant shift in the matrix to SIMD ratio, as there's a kind of a shifting set of operations that happens with length. And so if we look at the length profiles at length 64 and at length 2048, we can actually see that the main operation that many accelerators target, the matrix multiply operation, shrinks significantly. And we can see a very strong increase in the ratio of SIMD operations, in addition again to that kind of quadratic increase in runtime as a function of length. And so in summary, we can see that existing accelerators target shorter lengths, where we have a high matrix to SIMD ratio, which is common for downstream tasks like search and natural language processing. And additionally, these accelerators make use of weight stationary systolic arrays, which compute intermediate results and then store them into a large vector memory, or unified buffer it was formerly called. This is particularly efficient within compact representations, where the representations in the intermediate layers are kind of small. But unfortunately, within transformers, these representations also grow with length, meaning that within transformers, we actually see a really big increase in the area and power overhead of storing these representations in this vector memory. But one of the main things that we change about this in ProSE is that we chose to use output stationary systolic arrays, which allows for streaming. And this is a big gain that allows us to cut out a lot of this inefficient overhead, as we no longer have to cache these results. We can simply stream them through the accelerator all at once. And so at a high level, to really overcome these barriers within protein BERT drug design, we designed ProSE, our accelerator. And we can see that, again, here's that quadratic runtime as length increases, where we'd really like a flat curve. And existing AI accelerators are targeting these shorter lengths, but what ProSE is going to do is target these much longer lengths. Now, compared to a lot of previous work, which only focus on accelerating the attention mechanism, ProSE actually accelerates the bulk of the transformer runtime, which is the major advantage. And it's also transferable to NLP applications outside of biology, including recent work in long-length translation and document-length transformers, which are an emerging discipline within NLP. And so with those things said, I'm going to hand it over to Entropy, who's going to talk about the microarchitecture and some of our results.
Hi everyone, I'm Entropy Xu. I'm going to present the architecture part of the ProSE. To develop an efficient accelerator for this large-scale model, we start by zooming in the profiling showed by my co-author Ice before. We can see that all the operations can be broken up into two categories, the matrix multiplications and the SIMD, which includes all element-wise operations. In addition to that, the size of the matrix multiplications also differs a lot. There are very large matrix multiplications for the linear layers, and there are also many small matrix multiplications that is batched together for the attention mechanism. And this implies that we need an architecture that can efficiently compute both the large matrix multiplications and small matrix multiplications. So here, we have a typical 2x2 matrix multiplication, or you can also call it the gem operation based on name of function calls. We will use this A times B equals to C operation to illustrate our microarchitecture details. Before going into the ProSE, let's first take a look at the Google TPU. In short, the Google TPU is the weight stationary systolic array that uses a large unified buffer as intermediate storage. It performs all the element-wise operations using an activation unit. When executing a matrix multiplication, the weights are first preloaded into the processing elements, and then the inputs are streamed into the array. After the multiply accumulations are done, the output are then streamed out of the array and is then fed into the activation unit to perform element-wise operations. And finally, the data is streamed back into the unified buffer. This architecture works well for a typical neural network where there aren't too many element-wise operations. However, this data flow requires a whole complete global data flow for each element-wise operations. For consecutive SIMD operations, the data has to go out and in of the unified buffer for many times, which causes a lot of redundant data movement and therefore result in significant inefficiency for the long sequence length protein model we're working with. To solve this problem in ProSE, the first decision we made is to use an output stationary systolic array. Just like a typical output stationary systolic array, when we are doing matrix multiplications, the inputs are streamed in from top and from left simultaneously so that the processing elements are busy doing its multiply accumulations. We call this the matrix multiplication mode for our ProSE. However, remember we still need to do intensive SIMD operations. The method we use is to add a left rotating data path to each processing element in the array and add another SIMD ALU to the left of the array to handle all the vector operations. In the SIMD mode, the PE serves as the intermediate storage that rotates data to the left. The leftmost PE's output is fed into the SIMD ALU, and the output of the SIMD ALU is then fed back into the rightmost PE's input. Therefore, we perform an element-wise operation to all the values stored in each PE after a complete rotation. Compared to the Google TPU's global data flow, The local data flow implemented in our ProSE is way more efficient since it does not require the data to go through the entire chip. And consecutive SIMD operations can just be done by rotating multiple times. Also, since the protein BERT model contains Ceyu, softmax, and multiply additions, we implement our SIMD ALU using multiply adders and specialized lookup tables for these functions. Another architecture tweak we made is to use heterogeneous systolic arrays. As we mentioned before, we divide the model into 3 data flows, and each data flow requires different SIMD operations. For example, for data flow 1, we only need to do multiply accumulations in the SIMD ALU, and therefore we can remove the exponential function and the Ceyu to save space. Since it only does multiply addition, we call it the type M array. Following this approach, in our system, we include 3 types of systolic arrays, each responsible for one type of data flow. The type M array is for data flow 1, the type G array, which contains Ceyu unit, is for data flow 2, and the type E array, which contains exponential unit, is for data flow 3. Moreover, the optimum shape of the array to use for each data flow is different. Empirically speaking, the size of matrices in data flow 1 is usually large because it covers linear layers, and the size of the matrices in data flow 3, which covers attention mechanisms, are usually small. Therefore, choosing larger shape type M systolic arrays for data flow 1 and choosing smaller shape type E systolic arrays for data flow 3 will result in better efficiency. But how do we quantitatively determine the best heterogeneous configuration for ProSE? To answer this question, we designed a special design space exploration method. So, we mainly want to answer 2 questions. First, what shape of systolic array should we use for each data flow? Second, how many systolic arrays should we use for each data flow? We set the budget of the system to have at most 16K PEs. To further limit the number of designs we have to explore, we restrict the shape of the type M array to be 64 by 64 because we have empirically shown that smaller type M array will result in a configuration that is very far from optimum. In summary, all the possible hardware parameters are shown in this table. We swept through all the possible combinations of these parameters, and we have 238 design points at the end. We designed a performance model to obtain the performance of all the design points. We also synthesized all these design points using the 15nm technology library to obtain the physical characteristics of the chip. Incorporating these properties together, we plotted a scatter chart for efficiency versus performance. Here, we first show the chart for power efficiency versus performance. As shown in this chart, we picked 2 optimum points on the Pareto frontier, one for the most power efficiency and another for the best performance. We then plot for area efficiency. The best performance design is still the same one as we have shown in the previous chart. And to our surprise, the most area efficient design happens to be the most power efficient design. Putting everything together, the DSE produces 2 optimum design points, one for the best performance and another for the best efficiency, both in terms of area and power. The configurations for these 2 designs is shown in the table above. One last thing we need to do is to scale the whole system up. When we are comparing with GPU and TPU, we use these 4 parallel instances of either the most efficient or the most performance ProSE configuration. The result shows that when we are comparing to the NVIDIA A100 GPU, we achieve 6.9 times speedup and 48 times better power efficiency. When comparing to the Google TPU V2, we achieve 12.7 times speedup and 249 times power efficiency. When comparing to the Google TPU V3, we achieved 5.5 times speedup and 173 times better power efficiency. In conclusion, our ProSE system adapting to the long sequence length protein engineering model by implementing a left-rotating data path and exploiting the heterogeneous systolic arrays. The upward stationary left-rotating data path makes the SIMD-intensive networks more efficient by removing redundant data movements. And the heterogeneous array accelerates the protein BERT model by adapting to the different shapes of the matrix multiplications. This result shows that for protein models, designing very specialized hardware accelerator is still beneficial, even though ASICs for typical neural network models are already prevalent nowadays. Thank you for listening. If you enjoy our talk, please check out our full paper, and we welcome any questions.